Thank you, everyone. Thank you for coming. It is really my honor to introduce our keynote speaker for Q2B Paris 2023. He has conducted fundamental research in quantum mechanics. He proved nothing less than the fact that entanglement, which is the core of quantum mechanics, is real. And he has also been extremely instrumental in the creation of a vibrant quantum ecosystem in France and abroad with his unabated support. And I want to thank you for that. So please welcome once more with a big round of applause, Nobel Laureate Professor Alain. So Alain, I want to start with a question. How do you feel, how do you find it being here in a quantum to business conference, which probably is a bit different than the Swedish Academy?
Well, a major difference is that there is no king, no queen, and no princesses. I have not seen any princess in the audience.
We are in France, after all. So let's delve into the important part of the interview. I want to talk a little bit about entanglement, and I want you to give us like a brief history of entanglement from the beginning to your groundbreaking work in the 80s.
It's a long story.
It's a long story.
I think it started in 1935 with the paper of Einstein, Podolsky, and Rosen, and a few months later, a paper by Schrödinger. They recognized the extraordinary feature of entanglement. It was hidden in the formalism of quantum mechanics, which had been established by Heisenberg, Schrödinger, Dirac, but nobody probably had realized how surprising it is. What is surprising, and which was discovered by Einstein and company, is the fact that two entangled particles, even far away from each other, and in the spirit of Einstein, far away means separated in the relativistic sense. When two such particles are entangled, they seem to remain linked to each other. This is very surprising, and it gave Einstein an argument to claim that quantum physics is not complete. Quantum physics has declined by the Copenhagen school. He said the formalism is okay, but the interpretation of Copenhagen is not enough. One should complete quantum mechanics. Both disagreed, but for 30 years it was an unsettled debate, in my opinion. Because, after all, quantum mechanics was working and there was no disagreement on the way to use quantum mechanics, to do calculation, to interpret experiment. And it is John Bell in 1964, after the death of Einstein and Bohr, so we don't know what would have been their reaction. It is John Bell who found that if you follow the spirit of Einstein, the worldview of Einstein, then you come into contradiction with some predictions of quantum mechanics in some very rare cases, okay? So, in my opinion, these are the main steps in the conceptual point of view. Now, a few years after John Bell theorem, John Clauser and colleagues found a real practical situation in which one could test the Bell theorem, the famous Bell's inequalities. And it took another 3 years until Clauser and Friedman in 1972 did the first experiment demonstrating that some feature of entanglement are real. Should I go on?
I mean,
I am in 72, okay?
So I wanted to go back still a little bit in this period in the 80s where you did your experiments and just ask how aware were you of the importance and all the impact that your work would have in the decades to follow and everything that happened afterwards with entanglement?
Okay, before answering that question, I must say in which aspect, if I can say so, my work, the experiment I designed and performed, was adding something to the Clauser and Friedman experiment. It's in my experiment, I really addressed the question of non-locality. That is to say, the fact that the two entangled particles far from each other seem indeed to remain linked even at moments corresponding to space-like separated events. That is to say, no signal could allow them to communicate unless going faster than light, okay? And how did I realize that it was important? Well, I was a fundamental physicist, and settling a debate between Bohr and Einstein, yes, it is important. I thought it would be in the books of physics, which is the case, nothing else.
But after the experiments and a few years later, people started realizing the connections between entanglement and things like cryptography and quantum networks.
Yeah.
So how do you see all these developments and all the applications that entanglement had, which were much further from just physics?
Well, I must admit that I did not anticipate them, and it is in about 1990, 91, or who knows, that a young student in a conference sat in front of me and said, you know, Professor Aspe, with your entangled photon, one can do quantum cryptography. I say, what? Can you explain me that? His name was Arthur Eckert. So it was the first time I heard about possible applications. And you know, for me, I was very happy to have done this basic research, but thinking that it could be applied for something was more than a big cherry on the cake.
And where do you think we will be in 20 years from now when it comes to entanglement? People are starting to talk about, worldwide networks of quantum devices that can exchange entanglement and send messages back and forth. How do you feel about all of this?
You know, predicting about 20 years in advance is totally impossible. I have a very clear experience of that. When you are at CNRS every 4 years, you have to write a report in which you say what you have done and you say what you expect to do in the next 4 years. And when I go back to all my reports, I was about able to predict what I would do in the next 2 years, but then third and fourth year, it was different from what was anticipated. So I cannot make any prediction, but you mentioned networks. I think that for networks, there is an almost missing element. It's a good quantum memory. We need quantum memory for good teleportation. We need a quantum memory for quantum repeaters, etc. So I think when we have a good, reliable, practical quantum memory, then it will allow the deployment of such networks. And there is no fundamental law saying that you cannot have a good quantum memory. It reminds me of the development of nonlinear optics. Nonlinear optics at the beginning was just academic, okay? And at one point, people discovered crystals, BBO and stuff like that, which are really efficient non-linear crystal, and then the applications came.
Yeah. And when it comes to this quantum memory, just an extra question. As you said, the main challenge, is it that we need new science, or is the matter more of engineering and making these things work?
Well, probably we need a little more science, but what we need is development of new materials. And material is such a complicated thing that maybe when we have a quantum computer, we can design new materials.
Then we can do the memories.
But at the time being, we have to be pragmatic, try, and suddenly find one which is better.
So let's go into the quantum computers then. This is the next topic I would like to bring up with you. So everyone is trying to understand when we're going to have quantum computers, or how, or so I looked a little bit back at artificial intelligence, and if we look at when the first algorithms and the first models came out, it was sometime in the 80s. And then, we started talking about what AI can do in real life, maybe 2010, 2020. So there were like 30, 40 years between when we got some ideas on what to do and when we had the hardware to actually implement them. If we kind of try to move this to the quantum case, it says that maybe between 2025 and 2035, we'll start seeing what you call the second, let's say, quantum revolution, at least in the quantum computing part. How do you see this timeline, or what is, I know that you said you cannot predict 20 years from now, but how do we convince everyone to keep being in the journey towards the quantum computer?
Okay, when we speak about quantum computing, I think we must make the difference between quantum simulation with the famous noisy intermediate scale quantum computing and the all-purpose perfect quantum computer. The all-purpose perfect quantum computer, I don't think I will see it in my life, but I am not a young guy, okay? But I may be wrong. There could be a miracle happening that a small sub-ensemble of the Hilbert space is immune to decoherence, etc. But unless something like that happens, I think we are far from having the perfect, all-purpose, ideal computer. On the other hand, I am deeply convinced that the quantum simulators, such as the one of Pascal, by the way, I have a conflict of interest, okay, because I am a founder of Pascal, and I am an advisor of Candela, so it's disclosure, as I say, okay. I think that with a quantum simulator, as Pascal or Ion or who knows, we can solve real problems hard to solve with a classical computer. By real problem, I mean not a problem where you do something and you have something you observe and you say, oh, if I wanted to calculate that with a classical computer, it would take forever. No, I mean a problem which is a real problem that we know in advance and we bring a solution for that problem. We already are on the verge of that when Antoine Broes, in his laboratory, with his machine, which is, so to speak, the anticipation of Pascal. Pascal is a copy of the machine of Broes, but Broes is solving what is known in physics, what has been known for years, for decades in physics, as the Ising problem. It's a real problem, it does exist, and Antoine Broes gives a solution with his machine. So I think that we are going to have, not too long from now, similar results with problems which are yet more real. I think, for instance, something in which I believe is, or I think I find interesting, is the optimization of an electric grid. Okay, you have a production of electricity, there is wind is on and wind is off, sun you can predict, but anyway, and people plug their car here, plug their car there, and you have to equilibrate at all moments. I think this kind of problem could find an efficient solution with some machine, some quantum simulator. Well, this is just an example.
Yeah, so I guess, you know, this is also why we are all here, because we believe that we don't have to wait for the perfect quantum computer to get to the first applications. And you gave one example, which is some optimization algorithm or optimization problem on the power grid. Are there some areas where you think that quantum computers will be able to have useful applications before some others? And would it be more on the industry side or on the science side, for example, working with many-body physics or chemistry and stuff?
Well, I think both. If you can solve academic problems like the Ising problem, you can certainly solve some real problems. By real, I mean some problems for the society. Well, I think something should not be underestimated is what some people call the quantum accelerator. That is to say, a small component chip, if you want, that you put inside a classical computer and which improves something. So an example I love, although it seems trivial, is having a random number generator by sending a single photon on a beam splitter, and either it goes on one side or on the other side. This is the best random number generator in the world. I like to make, if you allow me, because a good random number generator is a generator of which no engineer, even the engineer who has built the machine, can predict the outcome, okay? And when a photon arrives on a beam splitter, nobody can predict if it goes on the side or if it is transmitted. Why nobody can predict? Because if somebody could predict, there would be hidden variables. And I have demonstrated that there is no hidden variable for single photons, you know? No, I love that. This looks a trivial example, but I am pretty convinced that there will be some circuits, maybe 6, 8 quantum bits, you know, solving locally a problem and allowing you to accelerate the quantum computer.
Within some more hybrid system that uses both classical and quantum resources.
But it's only a guess, okay? I'm not a magician. I mean,
but you, yes. So maybe one more question on the quantum computing is that many times when we talk about quantum advantage, we think about speed. Can we do something faster, right? But there are other things that quantum computers can offer, and you've been talking also a lot about, you know, energy, for example, or other. So how important are these questions to you, and also how do we deal with this new technology, right? And the fact that we need to come up with a way to responsibly develop new technologies.
Yeah, well, this is a concern of young people, and I was exposed to it the day when they announced the Nobel Prize 2022. There was immediately some event at Institut in my institute, and so the minister was here, everybody was here. But on the back of the room, there were the students of the Institut who were delighted to be here. But at the end, questions, and somebody raised the hand and say, okay, it's wonderful, but our concern, us young people, is about the planet. What do you think you can do for the planet? And then immediately came to my mind the fact that the machine of Antoine Brouès, you can plug it basically in any ordinary wall plug, okay? And so let's suppose it can solve a problem like the one of the electric grid. It's certainly much less energy than what you have in a HPC or something like that. So it's not more than that, but I think it's some idea to follow and to explore seriously. I doubt that, once more, the ideal purpose, full quantum computer, I don't know. But we may have simulator solving some niche problems, and for these niche problems, certainly more efficient than HPC.
Yeah. So let me go to a different topic now, and it's always really a pleasure to talk to you, because you're someone who has a very deep academic knowledge about quantum mechanics. At the same time, you don't shy away from more practical considerations, from things that have to do with even companies, investing in them, and so forth. I still think there is a gap between the two, between research in academia, in the university, and innovation, technology, and so forth. How do we manage to bridge the gap between the two?
Well, first by explaining all my students that if they have a good idea of application, they are not going to turn their hand. And I tell them that I regret that I understood too late that for an academic researcher, doing application may be interesting and grateful. I discovered that too late, and my mind is not directed towards the invention of applications. But I am convinced that it is useful. I'm delighted when there is an application, and this is why the founders of, for instance, Pascal, came to me. They are former students, and they came to me and said, oh, you encouraged us. Now, will you encourage us? Really means put some money in it, okay? There is no love without proof of love, okay? But I mean, it's important that academic people tell their students it's not doing a bad thing to go to application. And okay, I think it's the best thing. And I find that many startup companies have people who were in my orbit.
Indeed, I think there are many of your students here in the audience, and you have really created a new generation of quantum experts. And it seems like this is one of the biggest problems that we have or we are going to be facing, like the problem of competency. Like we do need more people to get into quantum science, quantum research, quantum engineering, and all of these things. And for that, we need more people to stay in academia and not everyone going to the industry. So how do we try to create this new generation of quantum competent workforce?
Well, first of course, it's a question of having positions for them. But we must also convince them that it is interesting. And I do my best. I can cite an anecdote about that. Years ago, a former student, he had a position at CNRS already, came in my office and said, "Look, Alain, when I was a student, we had two dreams, finding the Higgs boson and detecting gravitational waves. Now it's done. What is left?" And my immediate answer was quantum computer. And you know the name of that student? It's Antoine Broes, one of the leaders in quantum computing. So I think we have to explain to students that yes, there are so many things still to find and to explore, and we attract them.
Yeah, that makes the journey worth it. So we are already over time in the 20 minutes that we had, but we started 10 minutes earlier, so we do have some more time.
Wonderful.
So I will see if there are some questions, one or two questions from the audience.
I cannot see anything.
Yeah.
You know, when you are here,
actually,
you have sunlight and...
Yes, you can see us very well lit, but we cannot see. But if someone has a question, just shout it out.
Are you shy?
I will shout out a question at the MC. For Professor Aspect, were there times, your research took place over decades, were there times when you thought maybe this is the wrong track, or when critics said that this is not going to work out? How did you were there times like that, and how did you continue on?
Yes, of course. Well, you know, when I started in that research, almost everybody was telling me that it was wasting time. Everybody knows that quantum mechanics is working. Why do you want to check quantum mechanics another time? There are so many examples that it works, etc. But I thought that the discussion by Einstein was very convincing. What is good about Einstein is that all his articles are really crystal clear, okay? And his reasoning was crystal clear, and it was hard to realize that he might be wrong. So at least I wanted to test that. And then what I discovered what I found by thinking a lot about that is that entanglement is really different from all other features of quantum mechanics that have been settled, that have been discussed. Previously, for instance, the discussion between Einstein and Bohr in the Solvay meeting of 1927 was about Gedanken experiment involving one particle only, okay? And then Bohr always came with a good answer to Einstein objection. But now you had two particles, entanglement. And progressively, I realized that entanglement was really something new. And I think that one of the value of the work that John Clauser, Ed Fry, and I have done is putting the finger on the fact that quantum entanglement is different from previous feature of quantum mechanics. And I have a sign of that. The famous Richard Feynman, a fantastic physicist, in his famous lectures in physics, 1960, maybe 59, but let's say 1960, he writes about EPR. When you consider it from the same point of view that I developed in previous chapter, which is about single particle, there is nothing new, okay? 1960. 1982, Feynman writes a paper where basically he says, oops, I
was wrong.
I missed something. There is something different. It is entanglement. And Feynman, being Feynman, immediately he writes the first ideas about quantum computing. So if somebody like Feynman had not realized that it was different, that entanglement was different, then I think that I did a good job if I contributed to put the finger on that.
You did an amazing job, and you have the Nobel Prize to show for it. So let's just conclude here with the last question. We are at Q2B, which is a quantum to business conference. As we said, we're very happy to be in Paris to do this. So what do you think is the most important message that people can get out of these 2 days of interacting with each other?
Well, I think that it shows that France is a land for quantum research, quantum business, quantum innovation. I think it's a good sign of that, and I'm very happy to be part of it.
Thanks, everyone. Thanks so much, Alain.